drop a like and do share. Leave your comments and do not forget to subscribe for more videos.
Hello and welcome to Edupedia World.
Dear students, let's proceed with the chapter Hydrocarbon. So far we have completed the topic, general introduction, and then in the alkanes we have completed the nomenclature, the basic structures and the preparation. In this video we'll study about the properties, the physical properties and the chemical properties of alkanes, and in our next video we'll study about conformers. Proceed. Properties. So properties we will categorize as physical properties and chemical properties. So first of all, the physical properties. First, come to the nature. So alkanes are non-polar molecules, and why non-polar? Because the electronegativity difference of carbon and hydrogen is very less, and generally when carbon is attached to any other heteroatom like oxygen, fluorine, chlorine, bromine, iodine and nitrogen, then there is significant charge separation and the molecule becomes polar. Okay, so let's come back to alkane. So it is non-polar, so they will be held together only by weak van der Waals forces. Okay, so the weak van der Waals forces, it depends upon the size and the structure of the molecule. Okay, so larger is the size, the larger will be the molecular weight and larger will be the intermolecular force of attraction. Okay, so that will decide the nature, that is the physical state of the alkanes. For example, C1 to C4, okay, they have very weak forces, so they will be not held too closely, and so they will be in gaseous state. The next 13, that C5 to C17, they will have somewhat more stronger weak van der Waals force, so they will be in liquid state, and above that it is generally solid at room temperature. Okay, so 1 to 4 gaseous, weak, then 5 to 17 intermediate, so it will be in liquid state, and then above 18 it will be more strong, so it will be solid at room temperature. Next is the boiling point. Okay, since they are non-polar, so they will be held together by weak van der Waals forces, so they will have low boiling points. Okay, and there is a variation. Okay, so as the number of carbon atom will increase, so their molecular weight will increase, so their van der Waals forces will also increase, and hence the boiling point will increase. So we can say that with increasing number of carbon atom, the boiling point of alkane will increase. And there is a general observation that in a homologous series, with each increase of carbon atom, generally the boiling point will increase by 20 to 30 Kelvin. Okay, so this is graph which shows the variation in the boiling point. So generally the boiling point will be low. Why low? Because non-polar, weak van der Waals forces of attraction. Okay, and with increase in number of carbon atom, the boiling point will increase, because the van der Waals forces, they depend upon the molecular weight and increase with number of carbon atom. Okay, next, that is the melting point. In general, they do not show a regular variation as in case of melting point with increase in molecular size, though one correlation is visible, that the even number carbon atom will have the higher melting point as compared to the immediate lower alkanes with odd number of carbon atom. So you can see that C4 alkane is having a higher melting point as compared to C3, then C6 higher to C5, C8 is having higher melting point to C7. And why this phenomena is observed is like the even structure, they will be symmetrical. Okay, they will have more symmetry as compared to the odd structure. That's why they are packing. Means melting point is how they are packed. Okay, so the melting point will be decided upon the packing. So if it is even, so more symmetric, so more structured, so their packing will be more efficient as compared to the odd number of carbon atom. Hence, the attraction forces will be more, and because of that, the melting point for even number of carbon atom will be higher as compared to odd number of carbon atom. The simple reason is the packing. Because of the symmetry, packing is more efficient. So more forces of attraction, and hence higher melting point. Next is solubility. As we have studied earlier, it is non-polar. So since it is non-polar, so it will be insoluble in water, because water is a polar solvent. Okay, but it will dissolve easily with non-polar solvent, for example ether, benzene, or carbon tetrachloride. Okay, you should see that in carbon tetrachloride there are 4 carbon and chlorine bond. Carbon and chlorine bond, we have just seen that it will be polar. So how could this whole molecule is non-polar? So these bonds, CCl bonds, all the 4 bonds, they are polar, but they are a regular structure. So the polarity is cancelled out. All the dipole moments, they will cancel out and resultant dipole moment will be 0. You must have studied regarding this in chemical bonding chapter. If you have not, then please refer the videos. Okay, and so it is non-polar molecule. So any non-polar molecule, for example the alkane, it could be dissolved in carbon tetrachloride. Okay, and generally there is a trend that the solubility will decrease with increase in molecular mass. Okay, for example, let's see petrol. Petrol is what? It is the mixture of hydrocarbons. Okay, and since it is non-polar, so it will not get dissolved in water. Okay, next, density. Alkanes, they are lighter than water. Okay, their density increases with increase in number of carbon atom. Okay, so alkanes, they are lighter in water. As we have mentioned that petrol is a mixture of hydrocarbon. So you will see that petrol, they float over the water because they have low density as compared to water, and the density will increase with number of carbon atoms. Next is the chemical properties. Okay, so first of all, the substitution reaction. So substitute means we have to replace one atom by another. So here the replacement will be of hydrogen atom, and it will be replaced by any other heteroatom. For example, the halogens or the oxygen or the nitrogen, or like the nitro group or sulfonic acid group. Okay, or with like it could be alkane can be converted into alcohol. H will be replaced by OH, or for example, like it will be converted into carboxylic acid group, so H will be replaced by oxygen, and so on. So replacement means substitution reaction. Okay, so first of all, let's see the halogenation. So we'll replace one or more atoms of the hydrogen in the alkane with a halogen atom, or sometimes the carbon-carbon bond may also break. And it has been observed that the rate of halogenation will decrease down the group. Okay, and for the alkanes, for 3 degree is higher than 2 degree than 1 degree. 3 degree means the number of carbon atom attached to the carbon atom which we are viewing. For example, let's observe this. So this carbon atom is attached to only one carbon atom, so it is 1 degree. This carbon atom is attached to 1, 2, 3, so it is 3 degree. This carbon attached to 1, 2, so it is 2 degree. This carbon 2, so it is 2 degree. This again only one carbon, so whatever the number of carbon atom attached to that atom will decide the degree. Okay, whether it is 1 degree, 2 degree, or 3 degree. So let's come back to the halogenation. Okay, so halogenation, it is photochemical reaction in which we use the ultraviolet radiation, and then we'll take an alkane and then halogen. Generally, here we are taking chlorine, so it is a free radical reaction. Okay, so either one atom can be replaced, or 2 atom, or 3 atom, or all 4 could be replaced, or even in some cases the carbon-carbon bond, they also break at higher temperature. So let's see how the mechanism. So it is a free radical reaction. It will contain 3 processes: first the initiation, then propagation, and lastly the termination. The first initiation, like a homolytic cleavage of the chlorine will take place in presence of light ultraviolet radiation. Okay, will represented by H mu. Okay, and out of, there are 3 type of bonds: carbon-carbon bond, chlorine-chlorine bond, and carbon-hydrogen bond. Out of this, chlorine-chlorine bond is weaker as compared to carbon-carbon and carbon-hydrogen, so it will easier to break it. So first of all, the homolytic cleavage of chlorine-chlorine bond will take place, and we'll get chlorine free radical. Okay, so we have got the radical. Now it will propagate. Okay, so it will attack the alkane molecule. Here we had the methane, so it will attack the methane molecule, and it will break the weaker CH bond. Okay, and HCl will be formed, and again a free radical, that is the methyl free radical, will be formed. Okay, so again this methyl free radical is unstable, so it will attack the chlorine-chlorine, okay, bond. It is weaker, so it will break, and then halogenation takes place, and we will again have a chlorine free radical, and this process can carry on, and such chain reaction will lead to further higher. Again, this chlorine could attack on this molecule, and again it will attack on the chlorine molecule. So then 2 hydrogen atom could be replaced, then again 3, then 4 could be replaced. Okay, so finally let's come to the termination, how it will stop. So the reaction will terminate only when there will be no free radical. So either they combine, okay, like chlorine combine, or see this methyl can combine, or chlorine methyl could combine any way, and finally when there will be no free radical, then termination will happen, and the reaction will stop, or we can add some free radical capture. So this free radical could be captured, and then reaction will stop. So it's a free radical reaction, 3 process: initiation, propagation, and termination. Next is combustion. Combustion is simply heating in presence of air. Okay, so it's basically an oxidation process, and carbon will oxidize to carbon dioxide and hydrogen will oxidize to water, and this is highly exothermic reaction, so large amount of heat will be released. So you will study about this in thermodynamics chapter. Enthalpy of combustion, it's very high. That's why they are used as a fuel. Hydrocarbons, they are used as a fuel, like the petrol, kerosene and all. They contains large hydrocarbon, and that's why they are used as fuel. Okay, so this is the general combustion equation. We have balanced it. Okay. Next is controlled oxidation. Okay, in combustion there is no control. Okay, simply oxidation, but we can change the product if we regulate the supply of oxygen. Okay, and at a high pressure and in presence of a suitable catalyst, we get variety of oxidation product. Okay, for example, with if we pass the hydrocarbon alkane and air or just the oxygen in a hot copper tube, then we get alcohol. So ethanol could be prepared like this. Then similarly, the aldehyde could be prepared if molybdenum oxide is there, or we could get acid if we have the manganese acetate. Okay, so these are oxidation. So mild oxidation, then harsh, and then more strong oxidation. So, but generally, the alkanes, they are resistant to oxidation. Okay, by the oxidizing agents, but tertiary alkanes, they could be oxidized by the potassium permanganate. Okay, and with mild oxidation they could be oxidized to the alcohol. Okay, next, isomerization. Isomerism we have discussed in our previous chapter. Okay, you can refer that. Okay, so the alkanes, they can be isomerized, that is basically the straight chain could convert into branch chain when heated with in presence of the anhydrous aluminum chloride or hydrogen chloride. Okay, anhydrous AlCl3 and HCl. This will act as a catalyst and that will convert the N-alkane to something of branched. Okay. Next is aromatization. Okay. When you have the alkane containing 6 or more carbon atom, then with appropriate reaction condition, that is temperature, high pressure, and a suitable catalyst like in over the alumina gel. Okay, so this will provide the reaction site. Okay, it could be converted, alkanes could be converted into an aromatic compound. Okay, so we have discussed about aromaticity again in our previous lecture, so please refer those videos if you do not recall about these terms. Okay, so this process is known as aromatization, and here we have used various catalysts over the alumina gel. Okay, and then it has converted like 6 hexane, this 6 carbon atom, it will convert into benzene. And again we have discussed about the resonance over there. These are the resonating structure. If you do not recall, please refer the previous videos. Okay. Next is reaction over steam. So when we pass it over the steam, then for example the methane, and with a suitable catalyst like here we are using nickel over the alumina L2O3, then it could be oxidized to carbon monoxide and hydrogen gas could be evolved. Okay, and this acts as a fuel. Okay, so this methane plus carbon monoxide plus hydrogen, it is known as coal gas. Okay, which has a significant calorific value. Next is pyrolysis. Pyrolysis simply means fragmentation, that is heating at a very high temperature so that the bond break. Okay, so basically what we do is we heat a higher alkane at a very high temperature in presence of a suitable catalyst like alumina or silica. So fragmentation takes place and the higher alkane will break down into a lower alkane or alkene, and we get various products. So it is a good industrial method to produce lower alkene. Okay, and we are also getting a hydrogen. It's a fuel. Okay, and this method is known as fragmentation or cracking or pyrolysis, and this is a free radical reaction. Okay, so like pyrolysis of hexane could give like hexene or with 4 or 3 carbon atom, and various product could be achieved, and just by varying this temperature and the pressure or the catalyst, we can get the predominantly one of the product which we desire. Simply, if we do the fragmentation or the pyrolysis of kerosene, in kerosene, the chief component is dodecane, okay, C12, okay, and using any of the catalyst at high temperature, we can fragment this into the lower hydrocarbon, either alkane or alkene. Various products are obtained, and these are used as a better fuel. Okay, less amount of pollution will take place, and then the calorific value will be higher.